You know, the devices we use every single day, our phones, our laptops, the massive servers that hold up the internet, they're all built on principles that were laid out decades ago. So, to really understand the world we live in now, we've got to look under the hood and deconstruct the fundamental architecture of the computer itself. All right, so where do we begin? Well, we'll start with the most basic question of all. What even is a computer? From there, we'll dive into the 80-year-old blueprint that, believe it or not, still runs our world. Then we'll expose its biggest flaw, see how it's all built from tiny little switches, and finally, get to the core trade-off that every single computer designer has to struggle with. Okay, so at its most fundamental level, a computer is really a combination of two very different but totally inseparable worlds. You've got the physical stuff you can actually touch, and then you have the invisible instructions that tell all that physical stuff what to do. And this breaks it down perfectly. On one side, you have the hardware, all the physical bits and pieces, the silicon chips, the circuit boards. You can think of it as the body of the machine. But then on the other side, you have the software. These are the intangible instructions, everything from your favorite app to the operating system itself. It's kind of like the machine's consciousness, giving that hardware a purpose. So how is all of this actually organized? Well, the basic model for almost every computer was thought up by John von Neumann way back in 1945. I mean, think about that. It's a blueprint that's nearly 80 years old, and yet it is still the fundamental architecture of the very device you're watching this on right now. The first piece of this puzzle is the central processing unit, the CPU. It's best to think of this as the brain of the whole operation. This is the part that actually does the work, that executes the instructions and crunches all the numbers. Next up, we've got memory. And this is a really key insight from the von Neumann model. Memory is just one single shared space. It holds both the data that the CPU needs to work on and the program instructions that tell the CPU what to do with that data. They all live together. So, how do the brain and the memory actually talk to each other? Well, they communicate over something called a system bus, and you can just think of it as a shared highway, a big bundle of wires that connects all the major parts so they can send information back and forth. So you put those pieces together, and that's it. That's the von Neumann architecture. You've got a CPU, a single memory unit, and your input and output devices, like your keyboard and screen, and they're all connected over that one shared system bus. It's a beautifully simple and elegant design. But, and this is a really big but, that beautiful simplicity comes with a huge cost. This design has a deep, built-in flaw that has challenged computer engineers for decades. It's a fundamental performance problem, and it has a name: the von Neumann bottleneck. Remember that system bus, that shared highway we just talked about? Well, here's the problem. In the von Neumann model, it's a single-lane road. Every single piece of information, doesn't matter if it's an instruction for the CPU or the data that instruction needs, it all has to travel down the exact same path to get from memory to the processor. And that raises the big question, right? What happens when you get a traffic jam on that single-lane highway? The CPU is incredibly fast, and it's constantly asking memory for two things. What's the next command I need to run, and where's the data I need to run it on? And this conflict, right here, is the von Neumann bottleneck. Because the CPU shares that one path, it physically cannot get an instruction and get data at the same time. It has to do one, then the other. It has to wait. And that creates a hard limit on the speed of the entire system. And it doesn't matter how unbelievably fast the processor itself is. Okay, so we've got this major architectural problem, this bottleneck. To understand how we've tried to get around it, we have to peel back another layer. We need to go from this abstract blueprint all the way down to the physical reality of how these machines actually compute, right down to the microscopic switches that make it all happen. It all starts with the transistor. We're talking billions of them etched onto a modern chip, and each one is just a tiny, incredibly fast on-off switch. Now, by combining these switches in clever ways, we create what are called logic gates. These are little circuits that can make simple decisions. And then you combine those gates, and you can build complex circuits that can do math or even store a piece of data. And this table here shows you just how simple those decisions are. Just take a look at the AND gate. The output is only on, a 1, if both input A and input B are also 1. Otherwise, the output is 0. That's it. It's really that simple. And these fundamental rules are the absolute bedrock of everything a computer does. Now, building circuits out of these gates leads us straight into a central, inescapable conflict in computer design. It's this constant balancing act that engineers are always fighting, the architect's dilemma between speed and complexity. Here's the basic principle. Every time a signal has to pass through a logic gate, it adds a tiny delay. You could think of each gate like a toll booth on a highway. So, if you want to build a circuit to do something really complex, it needs more gates, which means more toll booths. And even though that circuit is more capable, the signal's journey takes longer, and the whole thing slows down. And here we can see it in action. A simple circuit with just one gate has a tiny delay. But when we chain 3 gates together to do something a little more complex, that delay more than doubles. It's a direct trade-off. You get a more powerful circuit, but you pay the price in speed. But there's a really powerful way to sort of cheat this trade-off. Instead of making one processing path longer and more complex, architects figured out they can just add more paths that work side by side, in parallel. This way, you can increase what the chip can do overall without slowing down any single path. This core dilemma has shaped computer design for decades. It's exactly why we have multi-core processors in everything from our phones to massive supercomputers. The idea is that it's much more effective to have several simple, fast processors, or cores, all working in parallel, than it is to try and build one single massively complex core that might actually be slower because of its own complexity. It's like choosing to build many fast highways over one winding, complex road. And all of this leaves us with a critical question about what's next. For almost 80 years, we've been building on a same basic blueprint, just finding more and more clever ways to fight its built-in bottleneck. But we are now approaching the absolute physical limits of how small we can make a transistor. So we have to ask ourselves, is this 80-year-old model going to last forever? Or will the future of computing require us to throw out the blueprint and invent a completely new architecture from the ground up?